Welcome back to Dr. Finance. This is a paper written by Herbert Simon, who won a Nobel Prize in economics in 1978. This is what he published in Quarterly Journal of Economics in 1956. A behavioral model of rational choice. Traditional economic theory postulates an economic man who, in the course of being economic, also rational. This man is assumed to have knowledge of the relevant aspects of environment, which, if not absolutely complete, is at least impressively clear and voluminous. He is assumed also to have a well-organized and stable system of preferences and the skill in computation that enables him to calculate for the alternative course of action that are available to him, which of these will permit him to reach the highest attainable point on his preference scale. Recent developments in economics, and particularly in the theory of the business firm, have raised great doubts as to whether this schematized model of economic man provides a suitable foundation on which to erect a theory, whether it be a theory of how firms do behave or of how they should rationally behave. It is not the purpose of this paper to discuss these doubts or to determine whether they are justified. Rather, I shall assume that the concept of economic man, and I might add of his brother administrative man, is in need of fairly drastic revision and shall put forth some suggestions as to the direction the revision might take. Broadly stated, the task is to replace the global rationality of economic men with a kind of rational behavior that is compatible with the access to information and the computational capacities that are actually possessed by organisms, including men, in the kinds of environments in which such organisms exist. One is tempted to turn to the literature of psychology for the answer. Psychologists have certainly been concerned with rational behavior, particularly in their interest in learning phenomena. But the distance is so great between our present psychological knowledge of the learning and choice processes and the kinds of knowledge needed for economic and administrative theory that a marking stone placed halfway between might help travelers from both directions to keep to their courses, lacking the kinds of empirical knowledge of the decisional processes that will be required for a definitive theory. The hard facts of the actual world can, at the present stage, enter the theory only in a relatively unsystematic and unrigorous way. But none of us is completely innocent of acquaintance with the gross characteristics of human choice or of the broad features of the environment in which this choice takes place. I shall feel free to call on this common experience as a source of the hypotheses needed for the theory about the nature of man in his world. The problem can be approached initially either by inquiring into the properties of the choosing organism or by inquiring into the environment of choice. In this paper, I shall take the former approach. I propose, in a sequel, to deal with the characteristics of the environment and the interrelations of environment and organism. The present paper then attempts to include explicitly some of the properties of the choosing organism as elements in defining what is meant by rational behavior in specific situations and in selecting a rational behavior in terms of such a definition. In part, this involves making more explicit what is already implicit in some of the recent work on the problem, that the state of information may as well be regarded as a characteristic of the decision maker, as a characteristic of his environment. In part, it involves some new considerations, in particular taking into account the simplification the choosing organism may deliberately introduce into its model of the situation in order to bring the model within the range of its computing capacity. 1. Some general features of rational choice. The flavor of various models of rational choice systems, primarily from the specific kinds of assumptions that are introduced as to the givens or constraints within which rational adaptation must take place. Among the common constraints, which are not themselves the objects of rational calculation, are 1. The set of alternatives open to choice. 2. The relationships that determine the payoffs, satisfactions, goal attainment as a function of the alternative that is chosen. 3. The preference ordering among payoffs, the selection of particular constraints, and the rejection of others for incorporation in the model of rational behavior involves implicit assumptions as to what variables the rational organism controls and hence can optimize as a means to rational adaptation, and what variables it must take as fixed. It also involves assumptions as to the character of the variables that are fixed. For example, by making different assumptions about the amount of information the organism has with respect to the relations between alternatives and payoffs, or optimization might involve selection of a certain maximum of an expected value or a minimax. Another way of characterizing the givens and the behavior variables is to say that the latter refers to the organism itself, the former to its environment. But if we adopt this viewpoint, we must be prepared to accept the possibility that what we call the environment may lie in part within the skin of the biological organisms. That is, some of the constraints that must be taken as givens in an optimization problem may be physiological and psychological limitations of the organism, biologically defined itself. For example, the maximum speed at which an organism can move establishes a boundary on the set of its available behavior alternatives. Similarly, limits on computational capacity may be important constraints entering into the definition of rational choice under particular circumstances. We shall explore possible ways of formulating the process of rational choice in situations where we wish to take explicit account of the internal as well as the external constraints that define the problem of rationality for the organism. Whether our interests lie in the normative or in the descriptive aspects of rational choice, the construction of models of this kind should prove instructive. Because of the psychological limits of the organism, particularly with respect to computational and predictive ability, actual human rationality striving can, at best, be extremely crude and simplified approximation to the kind of global rationality that is implied, for example, by game theoretical models. While the approximations that organisms employ may not be the best, even at the levels of computational complexity they are able to handle, it is probable that a great deal can be learned about possible mechanisms from an examination of the schemes of approximation that are actually employed by human and other organisms. In describing the proposed model, we shall begin with elements it has in common with the more global models, and then proceed to introduce simplifying assumptions and what is the same thing approximating procedures. 1.1. Primitive terms and definitions. Models of rational behavior, both the global kinds usually constructed and the more limited kinds to be discussed here generally require some or all of the following elements. Number 1, a set of behavior alternatives. Alternatives of choice or decision. In a mathematical model, these can be represented by a point set A. Number 2, the subset of behavior alternatives that the organism considers or perceives. That is, the organism may make its choice within a set of alternatives more limited than the whole range of objectively available to it. The considered subset can be represented by a point set A0 with A0 included in A. Number 3, the possible future states of affairs or outcomes of choice represented by a point set big S. For the moment, it is not necessary to distinguish between actual and perceived outcomes. Number 4, a payoff function representing the value or utility placed by the organism upon each of the possible outcomes of choice. The payoff may be represented by a real function big V of S defined for all elements S of big S. For many purposes, there is needed only an ordering relation on pairs of elements of big S, i.e., a relation that states that S sub 1 is preferred to S sub 2 or vice versa. But to avoid unnecessary complication in the present discussion, we will assume that a cardinal utility big V of S has been defined. Number 5, information as to which outcomes in big S will actually occur if a particular alternative, small a in big A or in big A0, is chosen. This information may be incomplete. That is, there may be more than one possible outcome S for each behavior alternative A. We represent the information then by a mapping of each element A in big A upon a subset big S sub A, the set of outcomes that may ensue if A is the chosen behavior alternative. Number 6, information as to the probability that a particular outcome will ensue if a particular behavior alternative is chosen. This is a more precise kind of information than that postulated in 5, for it associates with each element S in the set S sub A of probability P sub A of S, the probability that S will occur if A is chosen. The probability P sub A of S is a real non-negative function with the summation across big S sub A of probability P sub A of S equals to 1. Attention is directed to the threefold distinction drawn by the definitions among the set of behavior alternatives. Big A, the set of outcomes or future states of affairs, big S, and the payoff big V in the ordinary representation of a game. In reduced form, by its payoff matrix, the set big S corresponds to the cells of the matrix. The set big A to be to the strategies of the first player, and the function big V to the values in the cells. The set S sub A is then the set of cells in the 8th row. By keeping in mind this interpretation, the reader may compare the present formulation with classical game theory. 1.2. Classical concepts of rationality. With these elements, we can define procedures in rational choice corresponding to the ordinary game theoretical and probabilistic models. Big A, max-min rule. Assume that whatever alternative is chosen, the worst possible outcome will ensue. The smallest v of s for s in big S of A will be realized. Select that alternative small a for which the worst payoff is as large as possible. Big V hat of A hat is equal to minimum of big V of S, and where the S is in the set of big S sub A hat should be equal to maximum of the minimum of big V of S. Instead of the maximum with respect to the set A of actual alternatives, we can substitute the maximum with respect to the set A naught of considered alternatives. The probability distribution of outcomes, number 6, does not play any role in the max-min rule. Big B, probabilistic rule. Maximize the expected value of V of S for the assumed known probability distribution P sub A of S. The value V of V hat of A hat should be equal to the summation of V of S times P of S sub A hat. Summation across S in the set of big S of sub A hat should be equal to maximum of summation of V times P across with respect to the A in big A. Certainty rule C. Given the information that each small a in big A or in A naught maps upon a specified S sub A in big S, select the behavior alternative whose outcome has the largest payoff. V hat of A hat should be equal to V of big S sub A hat should be equal to max of V of S sub A with respect to small a in big A. The essential simplifications, number 2, chapter 2. If we examine closely the classical concepts of rationality outlined above, we see immediately that severe demands they make upon the choosing organism. The organism must be able to attain definite payoffs, or at least a definite range of payoffs to each possible outcome. This, of course, involves also the ability to specify the exact nature of the outcomes. There is no room in the scheme for unanticipated consequences. The payoffs must be completely ordered. It must always be possible to specify in a consistent way that one outcome is better than, as good as, or worse than any other. And if the certainty or probabilistic rules are employed, either the outcomes of particular alternatives must be known with certainty, or at least it must be possible to attain definite probabilities to outcomes. My first empirical proposition is that there is a complete lack of evidence that in actual human choice situations of any complexity, these computations can be or are in fact performed. The introspective evidence is certainly clear enough, but we cannot, of course, rule out the possibility that the unconscious is a better decision maker than the conscious. Nevertheless, in the absence of evidence that the classical concepts do describe the decision-making process, it seems reasonable to examine the possibility that the actual process is quite different from the ones the rules describe. Our procedure will be to introduce some modifications that appear on the basis of casual empiricism to correspond to observed behavior processes in humans, and that lead to substantial computational simplifications in the making of a choice. There is no implication that human beings use all of these modifications and simplifications all the time, nor is this the place to attempt the formidable empirical task of determining the extent to which and the circumstances under which humans actually employ these simplifications. The point is rather that these are procedures which appear often to be employed by human beings in complex choice situations to find an approximate model of manageable proportions. Chapter 2.1, Simple Payoff Functions. One route to simplification is to assume that V of S necessarily assumes one of two values, 0, 1, or of three values, 1, 0, minus 1, for all small s in big S. Depending on the circumstances, we might want to interpret these values as A, satisfactory or unsatisfactory, or B, win, draw, or lose. As an example of B, let big S represent the possible positions in a chess game at white's 20th move. Then a +1 position is one in which white possesses a strategy leading to a win whatever black does. Big A0 position is one in which white can enforce a draw, but not a win. Big A of -1 position is one in which black can force a win. As in the example of small a, let big S represent possible prices for a house an individual is selling. He may regard $15,000 as an acceptable price. Anything over this amount is satisfactory, anything less as unsatisfactory. In psychological theory, we would fix the boundary at the aspiration level. In economic theory, we would fix the boundary at the price, which evokes indifference between selling and not selling, an opportunity cost concept. The objection may be raised that although $16,000 and $25,000 are both very satisfactory prices for the house, a rational individual would prefer to sell at the higher price, and hence that the simple payoff function is an inadequate representation of the choice situation. The objection may be answered in several different ways, each answer corresponding to a class of situations in which the simple function might be appropriate. First, the individual may not be confronted simultaneously with a number of buyers offering to purchase the house at different prices, but may receive a sequence of offers and may have to decide to accept or reject each one before he receives the next. Or more generally, he may receive a sequence of pairs or triplets or n-tuples of offers and may have to decide whether to accept the highest of an n-tuple before the next n-tuples is received. Then, if the elements big S correspond to n-tuples of offers, big V of S would be 1 whenever the highest offer in the n-tuple exceeded the acceptance price the seller had determined upon at that time. we can then raise the further question of what would be a rational process for determining the acceptance price. Second, even if there were a more general payoff function, W of S, capable of assuming more than two different values, the simplified V of S might be a satisfactory approximation to W of S. Suppose, for example, that there were some way of introducing a cardinal utility function defined over big S, say big U of S. Suppose further that U of W is a monotonic increasing function with a strongly negative second derivative, decreasing marginal utility. Then V of S should be equal to V of W of S. Might be the approximation as shown on figure on page 107. When a simple V of S assuming only the values +1, 0 is admissible under the circumstances just as discussed or under other circumstances, then a fourth rational decision process would be defined as follows. D of D of 1, search for a set of possible outcomes, a subset S prime in S, such that the payoff is satisfactory. V of S is equal to 1 for all these possible outcomes, for all S in S prime. To search for a behavior alternative on A in A naught, whose possible outcomes all are in S prime, such that A maps upon a set big S sub A that is contained in S prime. If a behavior alternative can be found by this procedure, then a satisfactory outcome is assured. The procedure does not, of course, guarantee the existence of uniqueness of an A with a desired properties. 2.2. Information gathering. One element of realism we may wish to introduce is that while V of S may be known in advance, the mapping of big A on subsets of big S may not. In the extreme case, at the outset, each element, small a, may be mapped on the whole set, big S. We may then introduce into the decision-making process information gathering steps that produce a more precise mapping of the various elements of big A on non-identical subjects of big S. If the information gathering process is not costless, then one element in the decision will be the determination of how far the mapping is to be refined. Now, in the case of the simple payoff functions, +1, 0, the information gathering process can be streamlined in an important respect. First, we suppose that the individual has initially a very coarse mapping of A on S. Second, he looks for an S prime in S such that V of S is equal to 1 for small s in S prime. Third, he gathers information to refine that part of the mapping of big A on big S in which elements of S prime are involved. Fourth, having refined the mapping, he looks for an A that maps onto a subset of S prime. Under favorable circumstances, this procedure may require the individual to gather only a small amount of information, an insignificant part of the whole mapping of elements of big A on individual elements of big S. If the search for an A having the desirable properties of is successful, he is certain that he cannot better his choice by securing additional information. It appears that the decision process just described is one of the important means employed by chess players to select a move in the middle and end game. Let big A be the set of moves available to white on his 20th move. Let big S be a set of positions that might be reached, say, by the 30th move. Let S prime be some subset of A that consists of clearly one positions. From a very rough knowledge of the mapping of A on S, white tentatively selects a move A, that is, if black plays a certain way, maps on S prime. By then considering alternative replies of black, white explores the whole mapping of A. This exploration may lead to points S that are not in S prime, but which are now recognized also as winning positions. These can be adjoined to S prime. On the other hand, a sequence may be discovered that permits black to bring about a position that is clearly not one for white. Then white may reject the original point A and try another. Whether this procedure leads to any essential simplification of the computation depends on certain empirical facts about the game. Clearly, all positions can be categorized as won, lost, or drawn in an objective sense, but from the standpoint of the player, positions may be categorized as clearly won, clearly lost, clearly drawn, won or drawn, drawn or lost, and so forth, depending on the adequacy of this mapping. If the clearly won positions represent a significant subset of the objectively won positions, then the combinatorics involved in seeing whether a position can be transformed into a clearly won position for all possible replies by black may not be unmanageable. The advantage of this procedure over the more common notion, which may, however, be applicable in the opening of a general valuation function for positions taking on values from -1 to 1, is that it implies much less complex and subtle evaluation criteria. All that is required is that the evaluation function be reasonably sensitive in detecting when a position in one of the three states, won, lost, or drawn, has been transformed into a position in another state. The player, instead of seeking for a best move, needs only to look for a good move. We see that by the introduction of a simple payoff function and of a process for gradually improving the mapping of behavior alternatives upon possible outcomes, the process of reaching a rational decision may be drastically simplified from a computational standpoint. In the theory and practice of linear programming, the distinction is commonly drawn between computations to determine the feasibility of a program and computations to discover the optimal program. Feasibility testing consists in determining whether a program satisfies certain linear inequalities that are given at the outset. For example, a mobilization plan may take as given the maximum workforce and the steel-making capacity of the economy. Then a feasible program is one that not require a workforce or steel-making facilities exceeding the given limits. An optimal program is that one of the feasible programs which maximizes a given payoff function. If, instead of requiring that the payoff be maximized, we require only that the payoff exceed some given amount, then we can find a program that satisfies this requirement by the usual methods of feasibility testing. The payoff requirement is represented only by an additional linear inequality that must be satisfied. Once this requirement is met, it is not necessary to determine whether there exists an alternative plan with a still higher payoff. For all practical purposes, this procedure may represent a sufficient approach to optimization, provided the minimum required payoff can be set reasonably. In later sections of this paper, we will discuss how this might be done, and we shall show also how the scheme can be extended to vector payoff functions with multiple components. Optimization requires, of course, a complete ordering of payoffs. 2.3. Partial ordering of payoffs. The classical theory does not tolerate the incompatibility of oranges and apples. It requires a scalar payoff function, that is, a complete ordering of payoffs. Instead of a scalar payoff function, v of s, we might have a vector function v of s, where v has the components v sub 1, v sub 2, etc. A vector payoff function may be introduced to handle a number of situations. In the case of a decision to be made by a group of persons, components may represent the payoff functions of the individual members of the group. What is preferred by one may not be preferred by the others. Number 2, in the case of an individual, he may be trying to implement a number of values that do not have a common denominator. E.g., he compares two jobs in terms of salary, climate, pleasantness of work, prestige, etc. Number 3, where each behavior alternative A maps on a set of n possible consequences S sub A, we may replace the model by one in which each alternative maps on a single consequence, but each consequence has as its payoff the n-dimensional vector whose components are the payoffs of the elements of S sub A. This representation exhibits a striking similarity among these three important cases where the traditional maximizing model breaks down for lack of a compatible ordering of the payoffs. The first case has never been satisfactorily treated. The theory of the n-person game is the most ambitious attempt to deal with it, and so-called weak welfare principles of economic theory are attempts to avoid it. The second case is usually handled by superimposing a complete ordering on the points in the vector space in difference curves. The third case has been handled by introducing probabilities as weights for summing the vector components, or by using principles like minimaxing, simple satisfaction, or regret. An extension of the notion of a simplified payoff function permits us to treat all three cases in much of the same fashion. Suppose we now regard a payoff as satisfactory provided that v sub I is greater than or equal to k sub I for all I. Then the reasonable decision rule is the following. Search for a subset S prime in S such that v of S is satisfactory for all S in S prime, i.e. v of S of it should be equal to or greater than or equal to k. Then search for an A in big A such that S sub A lies in S prime. Again, existence and uniqueness of solutions are not guaranteed. Rule E is illustrated in figure 2 for the case of a two-component payoff vector. In the first of the three cases mentioned above, the satisfactory payoff corresponds to what I have called a value solution in a formal theory of employment relation, a comparison of organization theories. In the second case, the components of V define the aspiration levels with respect to several components of payoff. In the third case, in this case, it is most plausible to assume that all the components of K are equal. K sub I may be interpreted as the minimum guaranteed payoff, also an aspiration level concept. Chapter 3, Existence and Uniqueness of Solution. Throughout our discussion, we have admitted decision procedures that do not guarantee the existence or uniqueness of solutions. This was done in order to construct a model that parallels as nearly as possible the decision procedures that appear to be used by humans in a complex decision-making setting. We now proceed to add supplementary rules to fill this gap. 3.1. Obtaining a unique solution. In most global models of rational choice, all alternatives are equally evaluated before a choice is made. In actual human decision making, alternatives are often examined sequentially. We may or may not know the mechanism that determines the order of procedure. When alternatives are examined sequentially, we may regard the first satisfactory alternative that is evaluated as such as one actually selected. If a chess player finds an alternative that leads to a forced mate for his opponent, he generally adopts this alternative without worrying about whether another alternative also leads to a forced mate. In this case, we would find it very hard to predict which alternative would be chosen, for we have no theory that predicts the order in which alternatives will be examined. But in another case discussed above, the sale of a house, the environment presents the seller with alternatives in a definite sequence, and the selection of the first satisfactory alternative has precise meaning. However, there are certain dynamic considerations having a good psychological foundation that we should introduce at this point. Let us consider instead a single static choice situation, a sequence of such situations. The aspiration level, which defines a satisfactory alternative, may change from point to point in this sequence of trials. A vague principle would be that as the individual in his exploration of alternatives finds it easy to discover satisfactory alternatives, his aspiration level rises. As he finds it difficult to discover satisfactory alternatives, his aspiration level falls. Perhaps it would be possible to express the ease or difficulty of exploration in terms of the cost of obtaining better information about the mapping of big A on big S, or the combinatorial magnitude of the task of refining this mapping. There are a number of ways in which this process could be defined formally. Such changes in aspiration level would tend to bring about a near uniqueness of the satisfactory solutions, and would also tend to guarantee the existence of satisfactory solutions. For the failure of to discover a solution would depress the aspiration level and bring satisfactory solutions into existence. 3.2. Existence of solutions. Further possibilities. We have already discussed one mechanism by which the existence of solutions in the long run is assured. There is another way of representing the processes already described. Up to this point, little use has been made for the distinction between A, the set of behavior alternatives, and A naught, the set of behavior alternatives that the organism considers. Suppose now that the latter is a proper subset of the former. Then the failure to find a satisfactory alternative in A naught may lead to a search for additional alternatives in big A that can be adjoined to A naught. This procedure is simply an elaboration of the information gathering process previously described. We can regard the element of A that are not in A0 as elements that are initially mapped on to the whole set S. In one organism, dynamic adjustment over a sequence of choices may depend primarily upon adjustments for the aspiration level. In another organism, the adjustments may be primarily in the set A0. If satisfactory alternatives are discovered easily, A0 narrows. If it becomes difficult to find satisfactory alternatives, A0 broadens. The more persistent the organism, the greater the role played by the adjustments of A0 relative to the role played by the adjustments of the aspiration level. It is possible, of course, and even probable, that there is an asymmetry between adjustments upward and downward. The payoff were measurable in money or utility terms, and if the cost of discovering alternatives were similarly measurable, we could replace the partial ordering of alternatives exhibited in figure 2 by a complete ordering, an ordering in terms of a weighted sum of the payoff and the cost of discovering alternatives. Then we could speak of the optimal degree of persistence in behavior. We could say that the more persistent organism was more rational than the other, or vice versa. But the central argument of the present paper is that the behaving organism does not, in general, know these costs, nor does it have a set of weights for comparing the components of a multiple payoff. It is precisely because of these limitations on its knowledge and capabilities that the less global models of rationality described here are significant and useful. The question of how it is to behave rationally given these limitations is distinct from the question of how its capabilities could be increased to permit action that would be more rational, judged from the mountaintop of a more complete model. The two viewpoints are not, of course, completely different, much less antithetical. We have already pointed out that the organism may possess a whole hierarchy of rational mechanisms. That, for example, the aspiration level itself may be subject to an adjustment process that is rational in some dynamic sense. Moreover, in many situations, we may be interested in the precise question of whether one decision-making procedure is more rational than another. And to answer this question, we will usually have to construct a broader criterion of rationality that encompasses both procedures as approximations. Our whole point is that it is important to make explicit what level we are considering in such a hierarchy of models, and that for many purposes we are interested in models of limited rationality rather than models of relatively global rationality. Chapter 4. Further comments on dynamics. The models thus far discussed are dynamic only in a very special sense. The aspiration level at time t depends upon the previous history of the system, previous aspiration levels, and previous levels of attainment. Another kind of dynamic linkage might be very important. The payoffs in a particular trial might depend not only on the alternative chosen in that trial, but also on the alternative chosen in previous trials. The most direct representation of this situation is to include, as components of a vector payoff function, the payoffs for the whole sequence of trials. But then optimization would require selection at the beginning of the sequence. Of a strategy for a whole sequence, see the appendix. Such a procedure would again rapidly complicate the problem beyond the computational capacity of the organism. A possible middle ground is to define for each trial a payoff function with two components. One would be the immediate payoff consumption, the other the position in which the organism is left for future trials, saving liquidity. Let us consider a chess game in which the players are paid off at the end of each 10 moves in proportion to arbitrarily assigned values of their pieces left on the board, say queen 1, rook 10, etc. Then a player could adopt some kind of planning horizon and include in his estimated payoff the goodness of his position at the planning horizon. A comparable notion in economics is that of the depreciated value of an asset at the planning horizon. To compute such a value precisely would require the player actually to carry his strategy beyond the horizon. If there is a time discounting of payoffs, this has the advantage of reducing the importance of errors in estimating these depreciated values. Time discounting may sometimes be essential in order to assure convergence of the summed payoffs. It is easy to conjure up other dynamic complications which may be of considerable practical importance. Two more may be mentioned without attempting to incorporate them formally. The consequences that the organism experiences may change the payoff function. It doesn't know how well it likes cheese until it has eaten cheese. Likewise, one method for refining the mapping of A on S may be to select a parameter alternative and experience its consequences. In these cases, one of the elements of the payoff associated with a particular alternative is the information that is gathered about the mapping or about the payoff function. Conclusion. The aim of this paper has been to construct definitions of rational choice that are modeled more closely upon the actual decision processes in the behavior of organism than definitions heretofore proposed. We have outlined a fairly complete model for the static case and have described one extension of this model into dynamics. As has been indicated in the last section, a great deal remains to be done before we can handle realistically a more completely dynamic system. In the introduction, it was suggested that definitions of this kind might have normative as well as descriptive value. In particular, they may suggest approaches to rational choice in areas that appear to be far beyond the capacities of existing or prospective computing equipment. The comparison of the IQ of a computer with that of a human being is very difficult. If one were to factor the scores made by each on a comprehensive intelligence test, one would undoubtedly find that in those factors on which the one scored as a genius, the other would appear a moron, and conversely. A survey of possible definitions of rationality might suggest directions for the design and the use of computing equipment with reasonably good scores in some of the factors of intelligence in which present computers are moronic. The broader aim, however, in constructing these definitions of approximate rationality is to provide some materials for the construction of a theory of the behavior of a human individual or of groups of individuals who are making decisions in an organizational context. The apparent paradox to be faced is that the economic theory of the firm and the theory of administration attempt to deal with human behavior in situations in which that behavior is at least intendedly rational, while at the same time it can be shown that if we assume the global kinds of rationality of the classical theory, the problem of internal structure of the firm or other organization largely disappear. The paradox vanishes and the outlines of theory begins to emerge when we substitute for economic men or administrative men a choosing organism of limited knowledge and ability. This organism's simplifications of the real world for purposes of choice introduce discrepancies between the simplified model and the reality. And these discrepancies in turn serve to explain many of the phenomena of organizational behavior.